Hello, this is Team 1, and we will present about our project, Dreaming for Dreamer. We will first recap the last presentation, introduce our new approach, and then talk about implementation, results, and discussion. Before talking about our project, let me recap our two baseline papers. First paper is Dream to Control, Learning Behaviors by Latent Imagination, which is also called Dreamer. Dreamer is a kind of model-based approach and exploits an additional word model, RSSM, to infer a state of the environment. RSSM has those three components, and it encodes holistic information of the environment into a low-dimensional state representation. Dreamer firstly learns RSSM word model and make an imaginative simulation which enables optimizing value and actor network without seeing further through observation. The important thing here is that we can conduct multi-step prediction by the low-dimensional state representation and therefore can do stable and efficient learning. Our second paper is time-agnostic prediction, predicting predictable video frames. Time-agnostic prediction tries to discover predictable bottleneck frames rather than predicting at regularly spaced time frames. Predictor G takes context frames as input and produces a single frame GC. Then only the frame of the smallest loss is backpropagated. Since the smallest loss means the lowest uncertainty, repeatedly backpropagated frame becomes a predictable bottleneck. Using those two papers, our project Dreaming for Dreamer planned to train the RSSM word model with prior bottleneck information given from TAP model. By doing so, we expected TAP to help faster and effective word model training. But this has the serious problem that since TAP model provides bottleneck states of arbitrary time steps, so we cannot know which bottleneck states to use as a prior in inference stage. So we came up with another idea to use the bottleneck states of fixed interval time step. The difference from the TAP is that we can easily determine and manipulate the time step of the bottleneck states, and this can also solve the inference problem. While implementing the fixed interval method, we found the recent related work doing something similar to ours. They introduced a hierarchical video prediction model to learn long-term dependency, which is called clockwork variational autoencoders. Clockwork VAE consists of a hierarchy of recurrent latent variables, where each level transitions at a different clock speed. This figure shows how clockwork VAE works. Here the highlighted part is RSSM, and we can see that clockwork VAE extends RSSM hierarchically. This is similar to our fixed interval approach, which is to provide fixed interval bottlenecks when training the word model. So we changed our plan to try clockwork VAE in Dreamer, and this is the figure of how we are going to implement. As the level goes up, states include information of longer horizons, and those higher level states help the accurate long-term predictions. When implementing, we first concate all actions between previous and current states, then passed at once during each state transition. We expected that this would help more accurate training than just giving the previous one action.
Now I will explain the implementation part. We firstly explain the application of the original Dreamer, which is based on the RSSM word model. We use the open source code which is implemented based on PyTorch and test the model on DeepMind simulation package. Each experiment takes about 1 to 2 days on RTX 3090. This is the reproduction video of our word model on 4 different games. The first half of the video is posterior reconstruction, and the later half is the prediction of prior distribution. As you can see, the model can reconstruct the video well. but there are some misprediction of the prior distribution due to the underlying stochasticity of the agent. Now, let me explain the Dreamer code step by step. As mentioned at the previous paper review, Dreamer has 3 steps. The first step and second step, learning dynamics from experience and learning behaviors in imagination, is done in Dreamer class. In Dreamer class, there is a code where loss is defined. In the loss function, it firstly loads collected experience. Then the representation model gets prior and posterior distribution by a learning representation with given experience. Later, we should modify lower representation function. Using the prior and posterior distribution, image loss and divergence are calculated. Finally, the ELVA objective, which is used for optimizing RSSM, is calculated. Nextly, by using the above posterior distribution, imagination is conducted. Then actor, value, reward network are trained by using the feature of imagination. Again, later, we should modify the lower policy function, which conducts imagination. Finally, this is the part where environmental interaction happens. Firstly, with given observation, previous action and previous state, representation model gets the next state representation. Then by using the inferred state representation, the actor network decides what action to do next. Again, note that we should modify getState representation function later. To change word model from RSSM to CWVAE, what parts do we have to re-implement? As we repeatedly mentioned, the above 3 parts should be re-implemented. For example, at the first part, rural representation, the RSSM only takes single state representation. And the representation model only takes single observation and single action as input. To change this part into CWVAE version, we change the code to take multiple state representation. And we should change representation model to take multiple observation and multiple actions. The logic is similarly changed in the remaining lower policy and getState representation function. This is the changes of lower policy function, and this is the changes of getState representation function.
From now, I will talk about the results and the discussions. These are the simulator results of the prediction. The left is a result from original Dreamer and the right is our Dreamer. For the long-term prediction, the original Dreamer on the left shows a plausible prediction even though it is different from the ground truth. However, our Dreamer shows very diverse and unstable prediction in the long term. Numerically, the average reward of our model is very worse compared to the original Dreamer. Therefore, we can say that our hierarchical structure by CWVAE gives a bad influence to the latent space prediction. From now, we will explain the reason of this bad influence. First, this is the plot of the divergence of the lowest world model of ours and the original Dreamer world model. As you can see from the original Dreamer, the blue line, the divergence increases and then converges. This is a particular phenomenon in reinforcement learning due to the elbow loss that tries to make the prior and the posterior distribution to be similar. This increase in divergence means that it tries to find an appropriate distribution in a large search space. However, our model does not show this phenomenon. This means that our Dreamer does not find meaningful distribution and collapses to a meaningless modes. Especially, this collapse is worse for the models in level 2 and level 3 of our Dreamer. This shows that our hierarchy does not provide useful priors for the bottom level world model. The collapse in distribution also leads to bad training of our action model. From these training loss plots, we can see that the action model of our model is badly trained compared to the other parts, which are well trained like the original Dreamer. In addition, the plot of our world model in the right shows higher loss compared to the original Dreamer. We conjecture that this is because the state of the world model is good for reconstructing images, but bad to give the meaningful information to the action model, which leads to the bad training. To provide that our hierarchical structure confuses the training for the latent space prediction, we reduce the level from 3 to 2 and compare their performance. As the plot shows, our model with level 2 hierarchy show better results compared to the level 3 hierarchy. This shows that adding more hierarchy to our model confuses the latent space prediction even more. To enhance our model, we conjecture that we need an explicit way for the upper level models here to understand the sequence of actions from the bottom level model. Currently, we just simply concatenate the actions and pass it to the upper level world models, which is not enough for the model to predict the next state. By providing a better understanding, we expect that the world model can generate a meaningful state for the action model and the action model to predict a correct action. And lastly, I would like to conclude our work for the last 2 months. Our goal was to provide useful priors for the latent space prediction for the Dreamer. And then we extended the hierarchical structure of the CWVAE to provide such a prior. We trained our new Dreamer but failed to predict meaningful actions in the latent space. We conjecture that we can solve this problem by providing an explicit control for the hierarchical structure to help to understand the sequence of actions. This is the end of our presentation, and thank you for watching.